Since the last class, we started discussing about heteronuclear correlation. I discussed about what is heteronuclear correlation, a very basic pulse sequence where we can correlate any two different heteronuclei, proton carbon, proton nitrogen, proton fluorine, etc. But it could be abundant spin, abundant or dilute spin, whatever it is. We can do heteronuclear correlation. And I explained to you how heteronuclear correlation works in a simple pulse sequence. We apply for anti proton pulse, bring the magnetization to x-axis, and then allow it to evolve for some time. After T1 period, do an inept so that you create an antiphase magnetization for the proton, antiphase coherence, and then simultaneously apply to 90% proton and carbon. The coherence jumps from proton to carbon and detect carbon. A very simple experiment to understand, but it also is very easy to interpret. I said heteronuclear correlation do not have diagonals and are not symmetric because the chemical shift of different ranges are different. For different nuclei, they have different chemical shift ranges. So the two dimensions are entirely different, and there is no question of any symmetry or diagonal. Okay, that's one. These are the few advantages, and the interpretation is very simple. Sit on a peak in a Hetkar experiment. Go vertically up and horizontally. If this is the vertically, when you go up, if that is a proton axis, you get a chemical sheet of proton for that peak. And go horizontally, if it is a carbon axis, then you are going to get a carbon chemical shift. For example, if it is a CH3 group, you go vertically up, you get CH3 proton chemical shift. Go horizontally, you get CH3 carbon chemical shifts. And I showed one or two examples how we can interpret it very easily. But there is one drawback with this. Hetkar is a direct detection of the X nuclei. That could be very time consuming. Then new experiment has been invented and discovered over the years. People start doing different type of experiment to speed up the experiment and get better signal to noise ratio, and they are called inverse experiments. So I will from today start discussing about inverse experiments. Okay, so in the inverse experiment, as main problem I told you, the direct detection of X nuclei is less sensitive. Remember in the very first class or second class when I was discussing about sensitivity of detection of NMR signal, I said X proton is, let's say, is highly abundant, and compared to any other nuclei with highest gamma, and is more sensitive. And carbon 13 compared to that, I said 6,000 times nearly smaller, less sensitive. And if I want to detect the carbon 13 directly, it is even more difficult because less sensitive, abundance is small. So as a consequence, that will take enormous amount of time. On the other hand, why can't we detect X nuclei indirectly through proton? It is something funny. Instead of detecting carbon, why should I detect proton indirectly? There is a way we can do that. The advantage of that, if I do that, we are not detecting carbon, we are detecting proton. That means gamma is high for proton. Sensitivity is 4 times larger than that of carbon. The experiment is faster. But how we do is a challenge, we will do that. So direct detection of X nuclei may take, let us say, few hours, 10 hours, 15 hours experiment, whereas inverse detection experiment will take half an hour to 1 hour. See the saving in the instrument time, saving in your experimental time. There is enormous saving in the experimental time because we are not directly detecting the X nuclei. How do we do that? It's a very simple way. We do the polarization transfer through inept. This is always done from abundant spins to rare spin, dilute spin. Abundant spin, if we let us say take proton and carbon, abundant spin is proton, I give magnetization to carbon. Then I detect carbon, so then again we are detecting carbon. That's the problem. What we will do is, you will take the magnetization of proton, give it to carbon, and take it back from proton again. Take it back from carbon to proton again. You understand the problem? Give the magnetization from proton to carbon and take it back. In this process, I am detecting proton, but in this process, I get the information about carbon 13. Is the advantage. Directly I am detecting proton, high sensitivity nuclei, saving experimental time, but I also get the information about dilute spins. This is an advantage. And of course, I can do the decoupling experiment and do the a coupled experiment, a decoupled HSA, inverse experiment, everything can be done. That's all well known. So in the inverse experiment, in the two-dimensional experiment, usually detection dimension is proton, because I am directly detecting proton. That is sensitive nuclei. If I detect carbon-13, then it is not sensitive. No, it is not inverse experiment. It is a direct detection. It is like HETCAR. That will take more time. So in the inverse experiment, detection dimension is always proton. That saves time. Okay. And we have a number of experiments are there, which have been designed. For example, HMQC, heteronuclear multiple quantum coherence, HSQC, heteronuclear single quantum coherence, HMBC, heteronuclear multiple bond coherence. These are some of the common heteronuclear correlation experiments generally employed for analyzing the spectrum. What does HSQC does? HSQC gives connectivity between directly coupled heteronuclei, and it uses one bond heteronuclear coupling. For example, in a molecule like this, assume one bond coupling is 150 hertz. That is only for experimental purpose to set up. In a molecule like this, I can get a correlation between this carbon and this proton, or this carbon and this proton, doesn't matter. This carbon, this proton, this carbon, this proton. I can get the correlation information. One bond, directly bond, that is HSQC. And it uses the concept that there is a one bond coupling between carbon and proton. Heteronuclear J coupling, indirect coupling. And this can be any. I took the example of carbon. Does not make it mean it is only for carbon and proton. You can have a carbon proton HSQC, nitrogen 15 HSQC, any other nuclei dilute spin to any other abundant spin. One of them should be abundant spin, because you have to do the polarization transfer and detecting that nuclei as a sensitive nuclei. So you can have fluorine nitrogen, fluorine carbon, all sorts of HSQC experiments are possible. If I do nitrogen 15, I can get the correlation between one bond proton and nitrogen and proton, one bond carbon proton. In varieties of such experiments are possible. Of course, I also said one more, HSQC and HMQC and HMBC, 3 experiments. What is the difference between HSQC and HMQC? One is multiple quantum, through the multiple quantum pathway we adapt. Other is HSQC, single quantum. Both of them provide identical information. Small difference is there. In HMQC, you will also get HH coupling. There will be some homonuclear couplings among protons may also evolve. So small difference is there in the observation. As far as the appearance of the spectrum is concerned, except some couplings like HH coupling, others will also come through. As far as the heteronuclear correlation information is concerned, both of them give identical information. And if there are any differences between them, it is only small subtle differences are there. Okay. Let us see what about the long range couplings in carbon 13. You can also take the carbon 13 the NMR spectrum. I can get 3 bond coupling like this. I can get 3 bond, 2 bond, 2 bond like this. Varieties of long range couplings are possible. How do you correlate them? Is there any way I can correlate? In the HSQC I said, directly one bond coupling between carbon and proton, if it is there, I will correlate only directly connected heteronuclei. What about long range coupling with, if this proton, if it correlates to this in a molecule like this, is it possible? So not this one, this long range. Yes, it is possible. That is called heteronuclear multiple bond correlation. That means several bonds are remotely coupled. Between two nuclei, proton and or abundant spin, other spin, remotely coupled, can be correlated. Then what do you use here? In the HSQC, we use one bond carbon proton couplings. One bond coupling is needed for getting the correlation information. In the HMBC, we use long range correlation, 2 bond or 3 bond, which is from 0 to 10 hertz. Similarly, if I take CH coupling, 2 bond is also about 10 to 15 hertz. So this is also 10 to 50, 0 to 10 hertz like that. So we use long range coupling constant to correlate protons and carbons which are remotely coupled, long range correlation. For example, in a molecule like this, HSQC, I told you, it will give direct correlation like this. But HMBC gives correlation of this carbon to this proton, this carbon to this proton, and this carbon to even this proton 1 to 3 bonds away. And each carbon, this can give to this, like that. Varieties of correlations you can think of. HMBC can give long range correlations, one carbon to many other protons, now 2 bond, 3 bond separated also. HMQC makes use of multiple quantum pathway during evolution. That is the only difference. HMQC is slightly different from HSQC and HMBC. The only thing is, in the case of HSQC and HMBC, we use inept for polarization transfer. During evolution time, we use inept. So that is the advantage. We will gain here. Polarization transfer is there. So normally, HMQC very few people use, very rarely. HSQC and HMBC are commonly employed experiments. So we will start discussing HSQC, HMBC over in this class for some time. Try to take lot of examples. So HMBC gives cross peaks between protons and carbon that are 2 or 3 bonds away. And then you may ask me a question, if I have a molecule like this and I have proton here and this proton here, this can give correlation to this can give correlation. Whatever is directly bonded, that is also there. Will it not give correlation? Will it not confuse us? Then we do an experiment. We design the experiment in such a way the direct one bond correlation peaks are suppressed. We will remove this one, retain only long range correlations. One bond direct correlations we suppress and long range correlations are retained. That is what is done in HMBC. That is why it is called heteronuclear multiple bond. Multiple bond means separated by multiple bonds, remotely bonded. That correlation we can do. One bond directly bonded are suppressed. They are removed. So HMQC experiment, few subtle points to understand you. Subtle point is HMQC experiment is more robust as far as experimental imperfections and miscalibration is concerned. For example, slight deviation from 90-degree pulses, etc. There is an imperfection in the pulse experiment. HMQC is okay, tolerable. HSQC is more favorable when we want high resolution work. That is another information. You see, HSQC, if you want very high resolution, because HMQC generally gives broad signal, because of HH coupling which are coming into the picture, that will broaden the signal. Unless, of course, there are ways to remove the HH coupling by using several type of experiment. I will, if there is a time, I will discuss that also. But remember that usually gives broad signal because of homonuclear coupling among protons are also coming into the picture. So HSQC gives high resolution, more favorable for that. And suppression of the resonance, another important thing is we have to do. When I am correlating the carbon 13 with proton, I have to correlate this one with proton. But remember, carbon 12 is highly abundant, 99%. That's what I said. If I do an N15 proton correlation, nitrogen 15, nitrogen 14 is also there, that is 99% abundant. They give huge peaks. Somehow we have to reduce this. There could be signal coming from protons attached to carbon 12 and N14 abundant spins. We need to suppress them. Otherwise, very difficult to get correlation of less abundant carbon 13 to proton, because these huge peaks will interfere. How do you suppress that? There are ways of suppressing this. One way is by phase cycling, other way is by gradients. There are 2-3 ways. These two things we will discuss today. So we have to suppress protons signal bound to carbon 12 or nitrogen 14 by using either phase cycling or gradients. Okay. When I talk about the heteronuclear experiments like HSQC, HMBC, HMQC, you may ask me a question, are there any analogous direct detection experiments? Of course is there. HSQC is HMQC is nothing but head-car experiment. Very first thing which we discussed yesterday or in the previous class about head-car experiment. That is a direct detection experiment. analogous to HSQC. HSQC is faster because of polarization transfer, saves time, otherwise identical. What about remotely bonded HMBC experiment? I did not explain, but is there any identical experiment for direct detection? Of course it is there, and that is called COLAC, correlation of long range carbons. So, long range correlation is there. This is analogous to HMBC. There are also direct experiments analogous to HSQC experiment, inverse experiments, but direct experiment because nobody does these days. So, that is I am not discussing. But I will give you some information about coupled and decoupled carbon-13 HSQC. HSQC experiment when we do, we can do different type of experiment. This has been modified over years by various workers in the field. We can have a different type of experiment. We can get coupled HSQC, we can do decoupled HSQC, and decoupling in F1 dimension, coupling in F2 dimension, decoupling F2 dimension, coupling in F1 dimension, or decoupling in both the dimensions. Varieties of experiments are possible. We will discuss what is coupled and decoupled carbon-13 proton HSQC. Okay. I can do 1H decoupling in the T1, which removes multiplicity in the F1 dimension. I can do carbon-13 decoupling in the T2, again it removes multiplicity. Either way I can do, individually, or I can do both. Or I can do nothing and get the coupling information in both the dimensions. Everything is possible. We will understand that what is that experiment by taking a simple bond, CH bond. A simple assume hypothetical case, we have carbon-13 and proton. Take for example CHCl3. In CHCl3, we have carbon and proton directly bonded. Forget about Cl3. This is a CH bond I have written. What are the types of experiment we can do HSQC? I will show here. I will take the 1H spectrum of that first. What do you get? We all know if I take CHCl3, 1H spectrum gives a single peak, this one. This is from 99% of the molecule coming because of carbon 12 attached to proton. That is carbon 12 is NMR inactive, but only proton we are detecting, no coupling. What about 1% of the molecule which has got carbon-13? That is here, carbon-13 coupled to proton. One molecule is there, 1%. That will become a doublet because of coupling with proton. And that is what the peaks we are getting here. They are, I told you already, they are called satellites. So, if I take the proton spectrum of the CHCl3 molecule, we get one peak for C12H attached proton and two satellite peaks for carbon-13 attached protons. So, that is how it is. We go to the next one. If I detect carbon-13, of course, this directly gives you one bond proton carbon coupling. What about carbon detection? It will give only a doublet. As I said, when I am detecting the dilute spin, the question of satellites does not arise. I am directly detecting carbon-13. So, it will be coupled to proton, it will be just a doublet of equal intensity. So, if I detect the carbon-13 spectrum of this hypothetical molecule, we get a doublet intensity 50-50 because it is split into a doublet. Now, what is the separation giving you? This gives you J coupling between carbon and proton. Alright. Now, I will do one thing. I will do the detection of proton with carbon-13 decoupling. What will happen? I break this coupling, carbon-proton coupling. That will not be there. I remove it. I told you about decoupling long back. So, when I do the decoupling, carbon-proton coupling is broken and you get only a singular peak. So, this peak is already 99% intensity. With this, it will become 100% intensity. It adds to that. You get a single peak by breaking carbon-13 coupling. What about this molecule? Here I am detecting carbon-13 and I do proton decoupling. So, these two doublet will collapse into a singlet. 50-50% intensity will go. This will become 100% intensity for one peak. This is what we can do. We can do detect proton, do carbon-13 decoupling. I can detect carbon-13 and do proton decoupling. Both the experiments are possible. Now you let us use this and see how many types of HSQC experiment we can do. Look at this. In this dimension we have carbon-13. In this dimension we have protons. I will consider a situation like this. Coupled experiment, I am not decoupling in either dimension. What does it mean? I will get, like previous example, if I look for proton NMR, I get carbon coupling. If I look carbon NMR, I get proton carbon couplings. So both are possible. In this dimension for proton, carbon-13 satellites are there, 1JCH. In this dimension for carbon, simply split into a doublet, I get carbon-13 proton coupling. So this is the situation. In both the dimensions, they are coupled. Carbon and proton are coupled. This is called a coupled HSQC. When I do an experiment, this is called coupled HSQC experiment. I can do one thing. I can decouple in the F1 dimension. Which is F1 dimension? This one, written here. I can decouple in this dimension and then get the coupling in the F2 dimension. So when I decouple in the F1 dimension, what will happen? These doublets will collapse into singlet. So you get a singlet at the center. Whereas this coupling is maintained. So this is, in this dimension is still a doublet. Only in this dimension the doublet is removed and you are going to get a singlet exactly at the center because coupling is removed. This is called an experiment where decoupling is done in the F1 dimension, coupling is retained in the F2 dimension. What is the next possibility? You can think of a situation, decoupling in the F2, coupling in F1, decoupling only in the F2. What is F2? This one. If I decouple in this dimension, this coupling is broken and you get a peak exactly at the center. Because this dimension I am still retaining the coupling. This is called decoupling in the F2 dimension. What is the next possibility? Decouple in both the dimensions. Then what will happen? This dimension, this dimension collapse into a singlet and this dimension will collapse into a singlet. You get only a peak exactly at the center. One peak. This is what we saw in the Hetcar experiment. When we try to interpret, we always saw one contour and we went vertically up and horizontally and analyzed and identified proton and carbon chemical shifts. That is what normally is done. This is a decoupled experiment. Decoupled in both F1 and F2 dimensions. Okay, then how do you do this? You have got the idea now how we can do the decoupling experiment. We can have varieties of possible experiment. Depending upon the information that you want to derive, we can have different experiments. All right. Let us understand what is the basic HSQC pulse sequence. What is the basic HSQC pulse sequence? This much you know already. What is this? It is a inept sequence. We have seen that already. We understood 90 on the proton with 2 delays which we had to manipulate with respect to JCH and simultaneous 180 on this and then simultaneous 90 on this to transfer the coherence from proton to carbon and detect. That is what we saw that. That is an inept experiment where there is a polarization transfer takes place. That is called inept. And then in the heteronuclear spin echo, I told you, if you apply 90 pulse on only one of them, what will happen? You can break the coupling because that J coupling will refocus. That is what I said. Applying a 180 pulse in one of the channel in the heteronuclear experiment means you are breaking the coupling. You are doing decoupling, pulse decoupling you are doing. Then afterwards what happened? This is exactly reversed here. See, same thing. We came like this. Now we are going backwards. What do you call this one? This is an inept sequence, and this is reverse inept. That means you brought the magnetization proton to carbon, decouple it, and then take it back like this. So it is called a reverse inept. So HSQC is a combination of inept with a 180 pulse at the center for the T1 period to evolve, which results in decoupling, and then reverse inept. This is what it is. We take the magnetization from proton and transfer to carbon by inept, and then allow it to evolve in the T1 period with a 180 pulse on the center, which causes decoupling. It results in decoupling of carbon and proton, and then take it back to proton and then start collecting the signal here. While collecting that signal, you are doing decoupling. Look at this. I am collecting the carbon 13 signal and decoupling proton. What are you going to get? You get a decoupled carbon 13 spectrum. All protons coupled to all the carbons are removed. For each chemical inequivalent carbon, you said single peak. But in the process, what has happened? You have taken the magnetization of proton to carbon, decoupled here in the T1 dimension, and then take it back. Here you are decoupling. So T1 dimension also you are decoupling, T2 dimension also you are decoupling. That means, like what I showed you in the previous that 4 possibilities, you are getting the last one. You get only one peak at the center. Both the dimension coupling is broken. And this is what the basic HSQC pulse sequence does. Of course, don't worry about this thing. This has been discussed in the previous class. And then basic, we use a 2 pulse sequence. Why? I told you we have to suppress the carbon peak, proton peak coming because of attached to carbon 12. That is important thing. We have to suppress that. So what we do is we use what is called a phase cycle. Phase cycling I did not discuss in this course extensively. But remember, in one of the previous classes of my advanced course, I discussed about phase cycling. I discussed various things about pulse field gradient, etc. to select a certain coherent pathway. That's what phase cycling does. But anyway, without going into the details, remember how we do it. We do first 90-degree pulse experiment, and then we invert the receiver accordingly. And the second experiment we do with 90 minus x, and then take the difference between the two. This is what we do. In both HSQC and HMBC experiment, what happens? The mechanism of polarization transfer is identical. Doesn't matter. So this is what it happens. Transfer magnetization from proton to carbon. This is identical for HMBC also. Proton to carbon, allow it to spin the evolve, then do the decoupling whatever you want in the T1 period, and then reverse inept, take the polarization from carbon to back to proton, start detecting the X nuclei while doing proton. See, we are detecting proton. That is an advantage. Look at it. The sensitivity of the detection here, you are detecting proton and decoupling carbon 13. That's important thing. So this is what it is. So when another important point I wanted to tell you is, when the HSQC is recorded, all protons induce a signal, whether it is carbon 12 or carbon 13. System does not distinguish, and the instrument does not distinguish. You are going to get the signals from both these things. All protons will give a signal. The unwanted resonance is 99%. That if you suppress, you can efficiently detect the correlation of carbon 13. That's what I said. So interference of the C12 and N14 peaks have to be suppressed. This is where I said basic 2 pulse sequence, 90 pulse experiment associated with inversion, and then co-addition of the data will suppress the signal corresponding to abundant proton coming from attached to carbon 12, abundant spin. How do you do this? First experiment you do with 90 plus x, second experiment you do with 90 minus x, and then each time when you do, you change the receiver phase also accordingly. Afterwards, do the co-addition of the data. This is what happens. I will show you example how it works. Take an experiment 1 where I am doing an experiment with carbon 13 plus with the first pulse on carbon 13 is plus x. I get a signal like this. This is major thing coming, carbon 12 attached proton, and I am interested in this satellite peaks. Huge peak is coming, and then that will suppress this signal because the major component is coming from the abundant spin, C12 attached to proton. That is one thing. That is one experiment I will do with first pulse plus x. What I will do, another experiment where first carbon 13 pulse is minus x. What happens in that case? Carbon 13 satellites get inverted like this. How it works, everything is a different question. See, in the another experiment, I do the phase cycling with here is a plus X pulse, here is a minus X pulse. C12 signal remains same, C13 signal is inverted because we are looking at C13 coupling. Okay. What I will do, I will take the difference between these two. When I take the difference between these two, see, this component I am trying to suppress. And I retain only this signal. That's intensity will be better now. That's what we have to do. And that's how we suppress this. This is the way suppression by using what is called phase cycling. We suppress this by using phase cycling. But remember, this phase cycling does not suppress efficiently. Look at it. It's not very efficient. It gives some artifacts. There is some problem. To overcome that, another experiment is designed. Instead of the phase cycling, we use gradients here. And that is an interesting thing. See, everything is remains same, but only thing is during this time, after the T1 period, after 180 pulse, we use what is called a sort of a echo-like sequence. And during this echo time, one pulse is applied, and here another pulse is applied during this time, gradient pulse. That was very important. The G1 gradient is applied within the spin echo to refocus that carbon-13 chemical shift, and G2 is applied during inept for refocusing, inept refocusing period. What happens? The first gradient acts when carbon has a coherence P is equal to +1. This is what is important here. You see, here N and P peaks are there, coherence +1 and -1 it is called. Okay, that we discussed extensively in one of the previous courses. Here simply remember, G1 acts when the coherence is positive, P is +1, single quantum coherence. Then it will become G1 into gamma C. In the second gradient acts when the single quantum magnetization is P is equal to -1. The coherence transfer path is -1. Then multiplying with this, it will become G2 into minus gamma. And if I have to maintain a particular coherence pathway for HSQC, the sum of these gradients, phase induced because of this gradient, must become 0. That means G1 into gamma C minus G2 into gamma H should be equal to 0. If gamma ratio I know between proton and carbon is 4, I put this value for gamma. Now if I have to maintain the ratio of G1 and D2 for carbon 13, it is 1:4. If I make 1:4, this becomes 0. G1 should be 4 times, then this is 1, then it will become 0. So proton should be 1 times gamma, carbon should be this gradient pulse for carbon should be 4 times. Same way for nitrogen 15 like this. And we do this experiment, this is called anti-echo experiment. And when we do this, we select once N peaks, other time P peaks. And then when we do this experiment, applying the gradient once 4:1, once 4:-1. That means we select N peak and P peak. It is called echo onto echo method. We collect the signal by doing this and do the coding. This is what happens. Look at this thing. This is a first experiment without suppression, with phase cycling, and this is gradient. See the advantage? In the phase cycling, there is some disturbance here. Not completely suppressed, there is artifact. But in the gradient, C12 attached proton signal is completely suppressed. This is an advantage. So parent signal coming from carbon 12 is suppressed efficiently by pulse field gradients. So this is an experiment which is done, and then HSQC is recorded. So I am going to, time is up, I am going to stop here. So what we discussed today, we discussed extensively about HSQC experiment. I told you what is an HSQC experiment, what is HSQC pulse sequence, how it works we discussed. HSQC, as I said, we take the magnetization from proton, give it to carbon, and then take it back to proton and detect proton. In between, during the T1 period, I can apply 90 pulse to do the decoupling, and I'll detecting proton, I do the carbon decoupling, so that I'll get the carbon decoupled proton spectrum. So I can do the decoupling in both the sides, both the dimensions. So and I showed you various ways of doing the decoupling. You can have decoupling the F1 dimension or F2 dimension, or one of them, or both, none in both the dimension, or both the dimension decoupling. Varieties of possibles are there. But major problem comes in the HSQC experiment is parent signal coming from the carbon 12 attached proton or N14 attached proton. This we have to suppress by phase cycling with a 2-pulse sequence. Once we do plus X, once we do minus X, correspondingly you invert the receiver phase and coord the data, you will suppress the C12 peaks. That is not very efficient, but we will use the gradient method, and the gradient we know how to calculate. It should be 1:4 for carbon and 1:10 for nitrogen and proton. And then once we apply positive gradients for other time we apply negative gradient, and then we collect N peak or P peak. It is echo anti-echo method we adapt. Again coordinate data, then you will suppress the efficiently. And I showed that gradient method is better, suppresses the carbon 12 peak parent signal compared to nitrogen 15. So with this I am going to stop today, and in the next class we continue with this HSQC, and afterwards we will go to a different 2D experiment. Thank you very much.